Hello, welcome to our seminar of EEG-based biometric system with a custom design convolution neural network. First of all, I want to introduce Mr. Kaan Bakırcıoğlu. Kaan Bakırcıoğlu has graduated in Electric and Elektronik Engineering Department from Yaşar University in 2017. His graduation project was about the design of the 3D bionic hand controlled away from the globe. He took the financial support for this project within the scope of the scientific research project of the Yaşar University. In his undergraduate education, he has studied abroad to Slovenia, and in his master education, he was in Greece as a part of the Erasmus student exchange program. His master thesis was about the classification of the EMG signals via neural network with MATLAB. He also worked as a part-time research assistant in Yaşar University while completing his master in 2020. Currently, he's a PhD student in the same department. That his PhD studies is supporting by the 2244 industrial program, and he's working as a system engineer in Borg Wagner. The presentation is yours now.
Thank you, Mustafa Hocam. Today I will talk about the EEG-based biometric systems. As Mustafa Hoca said, this topic is our PhD subject. Mustafa Hoca and Nalan Hoca is my advisors, are my advisors, and we are preparing this project under TÜBİTAK 2244 industrial PhD program. And Cüneyt Güzeliş is our project manager. In this presentation, I will start with giving some information about EEG. This is the brain signals of ours. After, I will talk about what is biometric system and why EEG can be a good choice for these systems. What are the methods of collecting EEG and how EEG devices are working. And lastly, I will summarize our paper about designing a neural network for EEG biometric system. Our brain is working as command center. It sends, receives, and processes all the information in the human nervous system. There are 86 billion neurons in our brain. Whenever we think or move a muscle, these neurons activate with energy. This energy causes of the movement of the ions, and the moments of many ions at the same time is creating a wave. We can capture this wave with the putting electrodes to the scalp. Scalp is here, and we can put some electrodes to here. When this wave of ions reach the scalp and comes in touch with the metal of the electrode, it causes a voltage difference between any two electrodes. And recording of these changes in the voltage called EEG signal. To analyze the complex signal in a better way, we can separate it with different frequency bands. In here, you can see delta waves are slowest waves, and they are active when we are in the state of deep meditation or state of sleep without dreaming. In theta waves present during a deep sleep, they contribute to process and storage of memories. Alpha waves are active during a state of alertness. The control of mental activity and learning is correlated with them. Beta waves detected during a waking state, when our focus is involved in a mental abilities that needs making decision or finding solutions. And the gamma waves are the fastest waves and observed during state of that requires a high level of focus or concentrations. All these signals are contained information information for individuals, and it can be used to get information about owner of the brain signal. In the modern world, a number of accounts and passwords are grown too much, and it's hard to remember all of them. Also, people need to save access to their personal data. In 2015, one survey showed that 40% of people had some problem with hacking, and 7 in 10 people no longer trust password to protect their personal informations. Biometric is one way to identify person. It is intended to identify based on physical, psychological, and behavioral properties of individuals. For example, fingerprint, iris, face, or voice can be an example for them. Even though they are special for everyone, sometimes they are not completely safe. For example, a fingerprint can be stolen from a cup, or recording voice can trick the biometric systems. EEG brain signals can be solution to that kind of problems. In the late 1990s, researchers discovered that EEG is carrying genetically specific information, and it can be used to identify people. Some advantages of EEG are it cannot be forgotten or lost. Also, it cannot be obtained or stolen by external observers without human will, without the subject's will. In here, a biometric system must satisfy certain number of criteria, such as universality, uniqueness, performance, collectability, permanence, and acceptability. In the figure, you can see the comparison of EEG with other biometric systems. For example, fingerprints is easy to use and have long-term stability, but some users without finger cannot use it. And also, it's easy to steal someone's fingerprint. Also, face recognition have low cost to build the system, and it has high non-match rate. Also, there's a problem about the twins. EEG signals are very strong against fraudness and universal for every human, but noise on the raw data due to blink and eye movement can be challenge for the systems. In the figure, you can see how EEG-based biometric systems work. The purpose of the system is to separate people from each other while doing same task. EEG-based biometric system applications can be divided into two, identification and authentication. EEG signals is collected from the subjects, and after some signal processing methods, the identification system finds the matching client from the client pool and answer the questions, who is the client? And in the authentication system, responds to questions of the client, a specific person. For example, is the client is Cindy or not? If the client, if the answer is yes, it accepts the client to access the signal system, and if the answer is no, it's rejected. The most identification systems train classifier to find the best candidate using 1 to n matching, where n denotes the number of enrolled clients. Sometimes they are putting +1 to prevent the false access to the signal, and with that +1, if there's something, if there's no matching, also system there is no matching. Most authentication systems contracts personal classifiers for each client in the database and verify each claim based on the corresponding classifier using one-to-one matching. It can be easier to analyze the system by dividing it into two parts. First part includes method of collecting data and what are the features of the device for collecting data. And the second part is where algorithm works. This part includes neural networks, signal processing, feature extraction, and training methods. For first part, I will give some general information now. And for the second part, I will summarize our study and its results. To begin measure signals, the electrodes need to be allocated to regions on the scope by the standards of the globally accepted 1020 systems. You can see in the figure. Electrode labels donated with the capital letters represented the area of the cerebral cortex. The AF or PF is represent the prefrontal, Fs represent frontal, T for temporal, P for parietal, O for occipital, and C for central. Here, while odd numbers electrons are represent the left side of the brain, and the even numbers represent the right side of the brain. And each of the regions have different, in here you can see the regions of our brain, and each of the regions have different role in human life. The frontal lobe is responsible for problem solving, movement control, and resonance. The temporal lobes is interested in vocabulary, memory, and auditory system. The parietal lobe is involved in the sensory information, and occipital lobe, which allows the recognition of shapes, colors, and visual information. The mental functions or motor movements generally used to activate EEG signals for biometric system. In the literature, these texts mainly divide into three major categories: resting state, event-related potential, and intentional mental activities. We can separate them. The recordings generally are taken in sessions and separated by a chosen time to see effect of time on the brain signal. Also, controlled environment prefer to limit the external noise. As I said, data collection method can be divided into three major categories. The reason for that, all different type of brain activities may have significant impact on the signal. That is why for a reliable system, there are some defined tests to evoke the specific brain activities. In resting state, sorry, in resting state, the subjects are sitting on a chair in a calm way, without actions done physically or mentally. Eyes can be kept closed or open. We can separate both open stimuli with the closed stimuli to separate signal. In the sensory stimulus, generally called event-related potential. In this stimuli, signals are triggered by visual input or motor events. The P300 wave is such an event-related potential component obtained during the process of decision-making. To obtain evoked data, the subjects are asked to watch a series of fast flashings or moving pictures. P300 wave can be used for the person recognition, but for this kind of systems, external device needed to obtain that wave. So this may not be a practical system for identification. In the cognitive stimuli are more controllable than the resting state and potentially less complex than the visual sensory stimuli. EEG data is recording during the performance of mental tasks, including mathematics problems, geometric figure rotation, mental letter, and visual counting. To catch the voltage difference on the scope, at least 3 EEG electrodes needed. 2 for the measuring the changes in voltage across the scope, and 1 is used as a ground. Voltage difference between electrodes are in millivolt range, and the amplifier brings the millivolts in range where can we digitalize accurately. And with combination of high pass and low pass filters, noise can be reduced. In microcontroller, signal convert to analog to digital, and finally the transmission module data goes to computer to move on. We can extend the number of electrodes with using same logic and design multi-channel EEG device. In this table, we can see several types of EEG device used in literature. Some of the devices have up to 256 channels, and some of them have only 1 channel. Different type of device can be selected according to the purpose of the research. For example, wired and multi-channel device can be selected if preparation time is not an issue. However, if it's desired to develop a fast biometric system that allows the user to move freely, a device with 5 channels and wireless data transmission may be preferred. You can see differences of the 3 devices in the figures. In here, approximately 250 channel in the brain in the EEG device is called brain amp, and the electrodes are fixed to cap, and data is transmitted with the cable. In emotive, there are 14 channels, and they are communicated with channels are connected to Bluetooth module, and the data sent via Bluetooth to the computer. In the mind wave, which is the most practical in this field, it has only 1 channel and send it the data with Bluetooth also. Both devices are using batteries for power. I want to talk more about transmission methods. There are 2 different types of EEG headsets according to their data transfer. Wired EEG devices are more stable and they can transfer more data in certain time. But movements of the cable and electrodes can cause a noise in the signal. For the recording which need more freedom, wireless EEG headset can be used. But of course, during the recording, connection may be dropped and some data can be lost. In the figure, you can see 8-channel EEG device with battery and how it looks when attached to the cup. So designing this kind of device can be very practical and useful for EEG-based biometric systems. To develop a neural network for biometric system, we started with using open source datasets. Biometric EEG database is chosen for our study. This dataset collected by using low-cost EEG device, which emotive epoch, this device. That is a collection of EEG reports recording by 21 healthy subjects. While they experience 4 categories of stimuli, these are showing some images to subject to extract specific emotions, also flashing screen with different frequencies, and mathematical questions by the screen, and finally resting state with eyes open and closed. EEG signals are collected in pre-section, each section separated by 1 week to allow for analysis of the template aging, and 14 channel is used to collect data. We can see all signals from 14 channel in here. In here, raw EEG signals from the resting with eyes closed were used in this study. These signals are 120 seconds long. To get better result using the data in its best performance, the sliding window approach was applied. 5 seconds was chosen for the window size. Overlap period was 2.5 seconds. Result of the windowing, we got this matrix as a data, and we use with this data to train our network. In here, 14 is a number of channels, and 1280 is size of the window. And after that windowing, we got 2870 sample for 14 channel. Also, to compare effects of the channel number and placement, we create one more data set with only using four channels, which are F3, F4, O1, and O2. Again, we use same windowing technique to get matrix of 4 channels. After creating raw data from 14 channel and 4 channel, data normalized to help the training of the neural network about finding features on similar scales. In here, you can see separately from the signals from the responding channel. Due to limited sample number, 5-fold cross-validation method is used. After whole dataset was mixed once, it was divided into 20% for test, 80% for training, to be selected differently in each trail. We use the convolution network as a machine learning method. That is an alternation of the standard neural network for handling multiple arrays of data, such as pictures, signals, and languages. One significant feature of the CNN, which separated from other machine learning calculations, is its capacity to pre-process data by itself. In this manner, a lot of assets like time and computational power may not be spent in data preparing. CNN consists of multiple stack layers to create a complex architecture for classification. These layers are convolution layers, pooling layers, activation function, and fully connected layers. The result of 2 experiments are given on the left side. Result for 14 channel can be seen. It's reached to 72.71 accuracy. On the right side, you can see the result for 4 channel, and it reached to 83.51. And the time for elapses is almost half as expected. Moreover, the accuracy rates were increased approximately 10%, which show that our design CNN was more successful in extracting the meaningful information from the channel which we choose. To understand what are the results are saying, we can check the formulas of these ones. When we collect all correct classification and divide them to the total samples, we are reaching the accuracy of the signal. Also, it can called CCR, correct classification ratio. In precisions, number of true positive divided by the number of total true predictions. In other words, precision finds out the fraction of predicted positive is actually positive. The recall is true positive divided by the true positive and false negative. In other words, recall measures the model's ability to predict the positives. F1 scores combine the precision and recall of classifier into a single metric by taking their harmonic means. So, according to score table, also F1 score show that our algorithm's classification power is increased. From the table, we can see the comparison of some studies about EEG biometrics. The first 4 studies have high correct classification rate. However, they do feature extraction, pre-processing before the feeding the classifier, which increases the complexity. In this study, the raw data directly as an input, raw data used as an input directly, and convolutional encoder used for classifier, which is similar to the result is similar to our first experiment. And comparing the result of the previous studies with same data, these 2 studies use the same data which we choose, the BET data set. Our study performs in terms of the accuracy of 73.51, thanks to learning abilities of the CNN. For the future studies, we want to develop a low channel EEG device and transfer data by using Wi-Fi 5G. With that way, we can send raw data in a faster way. Also, between device and receiver, we want to use some encrypted communication protocols to increase the safety of the EEG biometric systems. And for the feature, to select the electrodes, we can use these electrodes in any combination, and we can find the optimum number of electrode and placements for feature, I hope. For the 5G module, we found some modules from the Realtek, and it supports the Wi-Fi 5G communication. And we will continue to working with that module to communication. These are my references which I use for this presentation. And if you have any questions, I can ask. I can reply.
Thank you, Kaan, for this good presentation. Is there any questions to Kaan from the listeners?
I have a question.
Sure.
Kaan, thank you for the nice presentation.
Thank you.
In your future research plan, do you have such a plan in the future? You will build up your own experimental setup, and then you will obtain your data set, and then proceed in that way. That is the first question. I have 2 other questions, but you may reply it.
Okay. Okay. Yes, our plan is to design our own EEG device and creating our own data sets and use this algorithm which we develop for the open source dataset. We want to use that algorithm with our own dataset.
Okay. In that setup, the EEG recording from human beings is get under some protocol. What I mean, the people will read some tasks or will do some jobs.
Yes.
Under this setting, you will record their EEG.
Yes, Cüneyt Hocam. We also search for which method we can use for the recordings, and we found that resting state have a good potential for the biometric systems, and it have good information about the subjects. Also, we are thinking that using some mental tasks like math problems or visual counting methods. In the literature, it shows that the both stimulus have a good response for biometric systems, and we can try to find suitable way for our EEG device and our algorithm.
Thank you. Last question of mine. Which type of machine learning methods you used? The convolutional neural networks, for instance, which models are more appropriate to handle EEG signals and capturing the information?
Yes, until now, with the comparison with other literatures research, we found that I think our way and convolutional network have a very good performance on the raw EEG data because in the convolutional network find itself about the how can I say? It's get the features from the raw EEG data by itself, and we don't need to waste time about the prepare the signal for the classification. And the problem with the convolutional network, we should try many steps about to finding suitable filter numbers or filter size. For this manner, with advice of your Cüneyt Hocam, we try to genetic algorithm to find the number of filters and size of the filters. We tried some basic CNN, which for face recognition, and it took almost 2 days to find the suitable numbers for the CNN. But we are using more complex CNN for our EEG dataset, which it can increase the time for finding numbers with genetic algorithm. But for future, we can try it for we can try that with the powerful computers.
Okay, EEG signal is a temporal signal. As we know, long short-term memory and other recurrent neural networks are appropriate for processing temporal signals. Maybe LSTM or recurrent versions of CNN might be tried.
Yes,
in this context. You can, I think, consider also this issue. For instance, in the table, as you show, hidden Markov models are used. These are it was one of the state-of-the-art model in speech processing. So maybe recurrent versions, recurrent models including recurrent versions of CNN, might be useful. You may try to use recurrent trend predictive neural network, for instance. You know it?
Okay, hocam. I know, and I can research more about it, and we can
Okay,
try
fine.
to develop.
Very nice. We can talk on it later.
Okay, hocam.
Thank you very much again.
Thank you, hocam, for your questions.
Thank you, Cüneyt hocam. Is there anyone who wants to ask questions to Kaan? I think there's no question as I see. Then Kaan, thank you once more about this good presentation, and thank you for everyone who attended this seminar. See you on the next seminar of our department. Thank you.
Thank you. Thank you for all listening.
We can start.